I am Marine for the VGS online tutorial service at UC Louvain. In a previous video, we have seen the logic of the triangles with the folded roof system and how to add supports. In this video, I will introduce the notion of self-stress. I will explain the concept of mechanism, isostatic and hyperstatic structures. Then, we will look at what a self-stress is, what it's for, and how to use it using several examples. First, I would like to remind you a concept that was already covered in one of the earlier videos. Every structure is made of nodes and bars, as you can see here. Each node is free to move according to certain degrees of freedom, usually in 2 or 3 dimensions. A structure is in equilibrium if the applied forces are balanced by the forces in the bars. In this video, I will only be working in 2 dimensions, so x and z. Each node will therefore be blocked at y perpendicular to a screen. To understand what a self-stress is, let's move on the first example. We have here a basic structure subjected to a vertical force along the z-axis. The structure has 2 supports. The first one, here, is a pinned support, so it's blocked at x and z direction. The second one, here, is a rolled support, so it's blocked at z direction. We can also see that the load, which is applied on this node, is blocked at y, so that we only work in 2 dimensions. Now I can create a panel here that I connect to the equilibrium evaluation to look at the information on our structure. We can see that we have a matrix 12 by 12. It says that we don't need any self-stress and there is no mechanism. We therefore have a statically determined structure. Now I can generate the form and the force diagram. We have here the form diagram and here the force diagram. We can see on the form diagram that all the outer bars, the red one, are in tension, meaning they have positive values, while the blue diagonal bar here is in compression with negative value. This is due to the load, which is applied upwards with positive value. Indeed, we can see here that I put 5, but for example, I can change and take -5, and we can see on the form diagram that all the outer bars, which were in tension, are now in compression and vice versa. Now, what's happened if I remove one support condition? For example, this one. It was a pinned support, and now I remove this one, so we have 2 rolled supports. We can see on the panel that we get a 12 by 11 matrix. It says that we don't need any self-stress, but we have one mechanism. A mechanism appears when there aren't enough bars to ensure equilibrium. This means the structure can move freely under certain loads or even without any load. In this case, the structure is unstable, so it can move horizontally. VGS cannot calculate the internal forces in the bars. Let's go back to the first example. So this support condition was blocked at x and z direction, and this one was a roll support. And now I will add a diagonal bar just here. So don't forget to modify here and set multiple curves. And now we can look at the panel. We see that we no longer have a 12 by 12 matrix, but 12 by 13 matrix. So it says that we need to add one self-stress. What does that mean? It means that when VGS tries to solve the equilibrium, the system is overdetermined. So there are more bars than necessary for stability. We need to impose a force on one of the bars to eliminate one unknown and return to an isostatic case that VGS can solve. Thanks to the self-stress, I will once again have as many equations as unknowns. So I add the self-stress. You go in this panel and choose self-stress. We see that we still need to give 2 pieces of information. The first one is the index. to indicate on which bar we are going to put the imposed force. So I create a panel, and in this case, I want to put the force on this diagonal bar, so number 2. And I connect it to the self-stress component. And the second information to give is the magnitude of the force. So I add a slider that I can edit to modify the value. Here, for example, the maximum I put 10 and the minimum -5. And I also connect it to the self-stress component. And now I can connect it to the evaluate equilibrium. And now we can generate the form and the force diagram. Here. I can also modify the value of the self-stress, for example, 5. And we see that the force diagram is changing. If, for example, I put 10, as I increase the value of the self-stress, the internal forces in the structure also increase. We observe that the structure is in compression at the outside, but now if I put a negative value, for example, -5, we see that it's the opposite, and now it's in tension. Let's move on the final example. I've built here a slightly more complex structure with 4 supports. You can see here. They are all wall supports, and you can see that every node is blocked at Y direction so that we only work in 2 dimensions. If we look at the panel, we see that we have a matrix 15 by 17. So as before, it means that we have too many unknowns in relation to the number of equations. As before, we need to add self-stress components to reduce the system to a statically determined structure. I applied the first self-stress on the bar number 2, so this one, and my second self-stress on the bar number 5, so this one. When it's done, we can generate the form and the force diagram. To sum up, self-stress allows us to solve hypostatic structures, especially those without symmetries, where manual analysis becomes more complex. A self-stress is an internal state of force within a structure involving elements in tension or compression, even without external loads. It becomes necessary when the structure has more bars than needed, making it statically indeterminate. By imposing a force on one or more bars, we reduce the system to an isostatic case that VGS can solve. I hope this tutorial has given you a better understanding of what a self-stress is and how to use it. I invited you to follow us in our series of VGS tutorials to learn more about structural design with 3D graphic statics. See you in the next video!